Welcome to the WALRUS Rover final presentation for the Intel-Cornell Cup Finals. My name is TJ Watson.
My name is Brian Eccles.
My name is Brennan McLeod.
My name is Tim Mirko.
My name is Mitchell Wills.
Today we are going to share with you an overview of our project. We will start by defining our problem and mission statement to motivate the rest of the presentation. The first recorded use of teleoperated robots for humanitarian aid was in search and rescue missions after the September 11th attacks. Texas A&M collected user feedback on their use and found that there were some key issues that we will seek to address. Robots currently on the market are limited by bodies of water in their path. Water absorbs communication signals, so robots cannot go into water deeper than several inches. They ran into this problem when exploring underground, where sections had been flooded, and had to deploy strictly water vehicles. These vehicles are targeted towards a specific aspect of the mission, not unlike their land vehicle counterparts. Ideally, a rover would be capable of both the land and water domains for expanded mission profiles. In addition to these limitations, robots on the market are expensive. The cost of an iRobot PackBot is around $180,000, and the competition is similar in price. This will get you a very reliable system, but you are limited to the payloads and extra options specific to that rover made by that company. There is little to no ability for you to make your own payloads or look for payloads from competing companies. We seek to build a system which addresses these problems. Our mission statement summarizes the problems we've examined. It is as stated, to create a highly configurable amphibious rover for search and humanitarian missions at a competitive cost. The picture you see here is an example mission scenario for the rover. You can see that the rover's path, seen here in red, has it travel indoors, which involves stairs, hallways, etc., outside in muddy and waterlogged terrain, through debris, and all of this teleoperated from a distance. This adds an additional challenge because the rover needs to have enough camera views and feedback for the user to be aware of the situation the rover is in while driving.
In order to solve this problem, we created the Water and Land Remote Unmanned Search Rover, or WALRUS Rover. The WALRUS Rover is a mobile robotic platform that can overcome difficult land terrain as well as deep bodies of water. Through our enhanced payload interface, the WALRUS Rover can be configured for missions ranging from humanitarian aid in an Ebola treatment unit to search and reconnaissance missions after natural disasters. Our low-cost solution is comparable in feature set to other platforms such as the iRobot PackBot and the Kinetic Talon. The WALRUS Rover consists of four main subsystems: drive, flipper, chassis, and top plate. In the top left, you can see the overall dimensions of the rover. They are 9 inches tall, 20 inches wide, and 25 inches long. For gap traversal, the length of the rover can be extended up to 42 inches by actuating all four flippers in the outermost position. In order to provide cooling to our electronics, all of the electronics on the top plate shown in the upper right are thermally pasted to the top plate. The bottom image shows a view of the inside of the rover, including all four flipper actuators and our high-power drive motors. Also inside the rover are all of our proprioceptive sensors, our custom embedded boards, which allow us to communicate with sensors and motor controllers. Lastly, the internal chassis houses 3 cameras for front, bottom, and rear views. Now we will move on to the evaluation of the WALRUS Rover and how we tested our system. Shown here are some of the metrics we used to test our rover. In order to generate these metrics, we met with several professionals in robotics, including engineers from iRobot and Olin Collin of Engineering. These requirements are intended to be comparable to other systems while still improving on some aspects, such as water traversal. As you can see, we have met all of our requirements except for weight with batteries and water speed. These requirements are still being improved, however, as we hope to have the rover achieve these tasks in the near future.
To fully test the rover's mobility limits in both land and water, we brought it to the New England Robotics Validation and Experimentation Center, or the NERV Center, at UMass Lowell. This is where many other military search and rescue robots like the iRobot PackBot are tested. We collected some videos of the tests conducted at the NERV Center and around our campus and would like to share those. First, we have the WALRUS Rover driving full speed at 7 feet per second indoors on carpet. It has no problems turning even with its aggressive treads. Next, we have the WALRUS Rover completing the NIST-certified symmetric step field course at the NERV Center. This was designed with help from first responders and is considered an accurate representation of average rubble at disaster sites. It is the most challenging land terrain offered at the NERV Center. This is the WALRUS Rover climbing up a NIST-certified 35-degree inclined wooden staircase at the NERV Center. Next, the WALRUS Rover tackles the NERV Center's NIST-certified crossing ramps course in a figure-8 pattern. The flippers can be positioned for a smoother ride, but the rover has no problem completing this terrain without the optimal positioning. The WALRUS Rover was also tested in an urban environment. This is the rover driving 4.5 miles per hour on a pavement sidewalk. This is a rover driving up an inclined grass hill at course speed with ease. And this is the WALRUS Rover climbing up an 18-inch ledge with help from its 4 flippers for added mobility. The rover's water mobility was tested at the Nerve Center's fording basin. Here you can see the WALRUS Rover seamlessly entering the water from dry land without additional configuration steps required. Additionally, the rover was tested at our Institute swimming pool. The WALRUS Rover can float and propel itself in water at a speed of about approximately 1 foot per second using its main tread drive. Two additional requirements set by the project were achieving a 1.5 hour runtime and a 975-foot line-of-sight communication range. To test battery life, the charge report of the batteries was reported over the battery management system. This data was collected while at the Nerve Center, and an approximate 3-hour runtime while housing 2 batteries was determined. Adding 2 more batteries to the WALRUS Rover can extend this operation time to about 6 hours. The communication range of the WALRUS Rover was determined by driving it in a nearby park until communications were lost. Video stream and control of the robot was possible up to over 1,000 feet, hitting that requirement as well.
Here you can see our user interface running in the Chrome web browser and controlled using a joystick. It uses a number of modern web technologies to provide a fully featured interface without any plugins. It features a primary camera display in the center and a secondary one in the bottom right. Both of these frames can be dynamically configured to display video streams from any of the 4 cameras on the rover. Additionally, in the top right, there is an interactive 3D model of the rover, which provides the operator a better understanding of the rover's configuration. There are also a number of diagnostic indicators in the bottom left, which shows the information such as battery status and motor current. Using our computer, we also provide supervised autonomy behavior to simplify operation. From one of the cameras on the rover, we get a 3D point cloud of the environment. From that, we apply a region growing algorithm to extract planes. By iteratively applying different ransack algorithms to these planes, we then estimate the model parameters of the staircase.
The WALRUS Rover boasts a number of options for payload communications. Connected directly to our main computer are 3 USB 3.0 connectors, 1 HDMI connector, and 3 Ethernet connectors. These connectors are IP67 rated for submersion up to 1 meter. In addition, the included DE2I 150 FPGA dev kit offers a number of other interfaces for payload communications, including general-purpose I/O, RS-232 and TTL serial, USB 2.0, Ethernet, HDMI, and VGA. For power, payloads can connect to one of 3 Anderson Spec Pack power connectors that offer different combinations of regulated 24, 12, and 5-volt lines and unregulated 32-volt battery power. Though the WALRUS Rover is a successful and capable platform, there are a number of improvements that can be made. One thing we've done is replace the pod drive shaft couplers with a new design, as the current couplers are weak and become damaged due to fatigue during heavy use. The new design uses a high-strength 2024 aluminum alloy to save weight and a new 4-fin locking mechanism, shown here, to distribute load and reduce fatigue. For future improvements, we would like to reduce our weight by undertaking a redesign of the chassis. Additionally, as our current water speed is less than our requirement, we would like to add cowlings to cover the treads that redirect unwanted upward thrust backwards to increase speed. Lastly, we would like to replace our static tread tensioners with dynamic tensioners that accommodate rock and gravel uptake by the treads. A dynamic tensioner would allow the treads to deflect when a rock becomes lodged between it and the pulley, reducing load on the drive motors. Next, we will go over some of the logistics of our project, including our timeline, budget, outreach, and sponsors. Though this project began as an idea back in August 2013, serious work started at the beginning of this academic year in August 2014. We used the Gantt chart shown here to budget our time throughout the year. Much of our first term included research, prototyping, and requirement specification. During our second term, we began mechanical and PCB design as well as software development. Our third term was devoted to manufacturing, assembly, and continued software development. And finally, our fourth term consisted of system integration and performance testing, as well as outreach. All in all, the entire project was completed in just under 9 months by a team of 5 undergraduate students. As a tool for search and discovery and humanitarian aid, We participated with the WALRUS Rover in a number of demonstrations to spread knowledge and support for the growing field of search and humanitarian robotics. We demonstrated WALRUS Rover at the Vecna Robot Race, the Cambridge Science Festival, and the Worcester Art Museum, as well as for a delegation of Turkish military personnel that visited our campus. In addition, WALRUS Rover has helped further WPI's involvement in research in Ebola treatment units.
Here is the final face cost of our system. Our choice to use higher cost components is driven by our decision to use industrial grade components over hobby components. We chose to use Maxim motors for our drive system in order to increase the efficiency of the system. Our custom PCBs were developed in order to create a more targeted solution to reduce complexities in our electrical system. We also chose to use a higher-end computer in order to allow the rover to perform more complex tasks. As a whole, our move towards higher-end components allowed us to create a more reliable system. We would also like to thank our sponsors who, without their support and guidance, we would not have been able to build the WALRUS Rover. If you have any questions, feel free to contact us at walrus@wpi.edu or check us out on the web at walrusrover.com. For more technical information, please check out our online chronicle at walrusrover.com, which contains our Intel-Cornell Cup semifinal presentation, as well as a chronicle of our progress throughout the year. Thanks.